the thanks Marco just made for the invitation and also the prize. So I must say it was an honor and also quite a surprise for me. So I must say, in my generation, there is a good number of young researchers in Poisson Geometry who have done beautiful works, probably better works than I. So I'm just the lucky guy for this week. So I will take this as an encouragement to continue my work. So kind of my research fortunately I have been working with many extremely good researchers, so it's impossible for me to list all the names, but I do want to mention two of them. So one of them is Professor Alan, so Alan Weinstein, who is my advisor. So it's exactly 10 years ago I met him, and we have been working on many things together, and a lot of my ideas are from the long time discussion with Alan, so thank you, Alan. And the other name I would like to mention is my professor from Peking University who introduced me to Alan. I would like to thank him. So his name is Chen Ming. Probably not many of you heard his name, but I'm sure you have heard his student's name a lot in this conference. So almost all Chinese names I've heard are his students. So let me talk about my title. So my talk today is about Maxim Machine and kind of duality of gerbs and orbifolds. So the Maxim Machine, so it was kind of developed by George Mackey around 50s. So it was about representation theory. It's a kind of induction theory in representation theory. And the duality of gerbs, I guess we've already heard from Marco about gerbs, so this is kind of geometry. So the reason we are coming to these two subjects together is inspired by a kind of a conjecture made by some string theorists. So what they find out is if we are given a kind of a G-gerb on an orbifold, then there's a natural construction I'm going to explain to you today. We can construct a new orbifold with a kind of a B field, a U1 gerb on the orbifold, and what they conjectured was this kind of duality between the conformal field theory between these two sides. So that is the kind of conjecture leads us to this project. And what we found out is this Maxim machine, in particular the groupoid generalization of this Maxim machine, is a very useful tool to study this problem. And that's the goal I would like to explain to you. So this is a joint work with Xiang Tang. So he was also a graduate student at Berkeley, and very interesting. We were both, same time at Berkeley, and each of us wrote a thesis related to orbifolds, but in a quite a different flavor. So what we are trying to do in this project is so Xiang Hua is more like algebraic geometers and symplectic topologists, and I'm more into Poisson geometry and noncommutative geometry. So what we are trying to do is to combine the strengths of the two subjects to study orbifolds, in particular this problem. Okay? So here's the plan for my talk. I would like to use the first part of my talk to explain to you what Maxim machine is. And the second part, I will explain to you the second part of my title, the gerbs, groupoids, orbifolds. And the third part, I will try to present you some results we can obtain about this duality problem. Okay. So let me start with the first part about the group extensions. So this part of the story I will only focus on Maxim machine, and this kind of story has been developed into a much more powerful framework. It's a big subject in representation theory. And so this is basically about this induced representations, goes back to Frobenius and Schur in their study about permutation groups, representation theory of permutation groups. And the type of Maxim machine, or this induced representation theory I want to talk today, was formulated by Clifford. in the 20s, in the 1920s. Okay, so this slide is probably a quick review about undergraduate group theory. So what I would like to study is an extension of finite groups here. So this is G is the normal subgroup of H, and Q is the quotient group. Okay, and we would like to study the structure of H, try to use G and Q to express the information of H. So given us an exact sequence of groups, more general exact sequence of some structures, what we are usually trying to do is to determine whether this sequence split or not. So to do that, first step to do is we're going to try to find a set theoretical map to go from Q to H. That is what I'm writing as S. Okay. So with this section, what we can find is we can define this kind of action of Q on G through this section map S. So this is almost a group homomorphism of the following map. Q to automorphism of G. But unfortunately, this map alpha is not a group homomorphism. And the failure of this alpha being a group homomorphism is controlled by this kind of a 2 cocycle on Q with valued in G. Okay? So you can, and all this cocycle C can be written using S, and then you can find this homomorphism property of alpha is twisted by this 2 cocycle. Okay. And you can even try to write out the further properties, more refined properties about C's, this kind of cocycle conditions for C is more complicated because G now is in general not abelian. Okay? So that is the starting point of we're having kind of a structure theory about the extensions. So now I would like to explain to you this Maxim machine. So the idea of a Maxim machine is basically we are interested in the representation theory of the big group H. So the hope is we can use the representation theory of G and the Q to reconstruct the representation theory of H. So that is the kind of the program Maxim developed. So here I wrote the first natural idea we can do about a representation of H. Basically, we restrict it to be a G representation. Okay? So H acts on V, so G also acts on V, and we can try to decompose V into subspaces and sub-representations of G. Okay, so here, V row is the collection of all the G irreducible representations isomorphic to the class rho. So there may be more than one copy of the irreducible component of G. So we're collecting them together. That's the most natural way to group them. And the G hat is usually called this punctuating dual of the group. It's the isomorphism classes of irreducible representations. Okay. So that's kind of the first step. When we want to study, we restrict our original H representation to G representation. Okay. Of course, we know this kind of first step won't be sufficient to really rebuild the construction, the H representation. We need to definitely include the information from the quotient group. So that's the second step, is the kind of a more interesting step. So in this step, first the observation we can have is, since G is a normal subgroup of H, so the H acts on G by conjugation. And such an action induces an action on this punctuating dual, this G hat space. Okay? And we also know that the G acts on G hat trivially, because G acts on G by inner automorphism. this map pass through inner. And this inner automorphism acts trivially on the isomorphism class of reducible representations. So because of that, we can pass through the quotient to have a true action of Q on G hat. So remember we said Q doesn't really act on G as a true action, but now at the punctuating dual space, Q really acts on G hat. Okay? So that is the first observation, and now according to this observation, we can even look at the following structures. So remember, we have this decomposition of V into sub-representations of G. So now I would like to look at the Q action on this space. So that is the purpose of the next identity. So what do we find is, if we look at the orthogonal projection from V to V rho, we find if we started with the subspace rho, this H in the group H map rho to H rho. It's kind of shifting it's mapping the subspace of V rho to subspace of H rho, VH rho. So it's kind of mapping the different components. Okay? And in particular, from this identity, what do we can conclude? We can see that if our representation V is irreducible, if V is irreducible, the type of G representations showing up in this V must form an orbit of the Q action. There cannot be two orbits, because once you have two orbits, the representation naturally can be decomposed into two sub-representations. Because of this property. Okay? And this also tells us what? In order to study representation theory of H, we can reduce ourselves to study representation theory to this orbit, together with the representation of this subspaces V rows. Okay? Now that's kind of usually called the first step of Maxim machine. We reduce the representation to every orbit. And the second step in the Maxim machine tells us how to really classify the representation, irreducible representation of H associated to every orbit. So on every orbit of Q action on G hat, this is, because it's orbit, the restrict group point is transitive. So what I will do is I will take an easy step to choose a representative one point in the orbit and take the stabilizer group. And we know this group is Morita equivalent to the whole restriction of the action group point to that orbit. So this is kind of passing to the Morita equivalence. And then the statement of the irreducible representation of H associated to this orbit theta can be classified by the representation theory of this Q theta, the stabilizer group. But very interestingly, this is not classified by the standard representation of Q theta. Is a kind of twisted representation by Q theta. This is usually called the projective representation theory. Okay? So I will explain to you in the next slide what is this tau theta and what do I mean by twisted representation. Okay? So any questions? Okay. So in order to introduce this tau theta, we have to look at the representation theory in a slightly, more carefully. So what do we do is, remember we know this Q theta fixes a point rho in this orbit. So Q rho map rho to rho. What does this tell us? This tells us the following isomorphism of G representations. So originally, what we have, say, I have this representation. E rho is the G irreducible representation associated to rho, and this we have a map, a homomorphism from G to out of E rho. Now, we can try to write out this action Q rho. This is usually written in the following way. We are twisted the action by composition with the action alpha. Okay, so maybe I write this as alpha of Q. Okay. Remember, alpha Q is a automorphism. So alpha Q is automorphism of G. I'm composing it with E rho. This is going to give me another map from G to automorphism of E rho. And what we are saying is these two representations are isomorphic. Okay? And remember, this is a irreducible representation. If these two representations are isomorphic, this tells us there must be an intertwining operator to change E rho to E rho to stand to. This tells us the following. There exists, that will be this EQ. So let me EQ such that we have E rho composed with alpha Q can be written as EQ composed with E rho composed with EQ inverse. And EQ is a map from E rho to itself. Okay? So that is the kind of first step we do here. So we have E rho and this data EQs. The second observation here is we know that TQ will preserve V rho, so we can look at the representation of the Q theta on this subspace V rho. So another natural observation from representation theory is if we have V rho, it can always naturally, as a G representation, decomposed into the E rho tensor Hom G equivalent homomorphism from E rho to V rho. Okay, so that is the decomposition I'm writing down here. So I'm writing V rho as a tensor product of two vector spaces. And by Schur's lemma, so we can really prove TQ must act on this space V rho in this form. There won't be any mixing terms. So that is a kind of the first property we can prove. And furthermore, what you can prove is this composition operator acting on E rho commute with G action. So this is by some simple computation of representations. And remember, we know G action on E rho is irreducible. Any intertwining operator with a irreducible representation must be a scalar. So this gives us the property that this whole operator must be a scalar operator. So we are taking it's a U1 valued number here. And that is the core cycle we are introducing for this representation Q theta. Okay? So now what do I mean by twisted representation? Twisted representation basically means we have FQ1 composed with FQ2. Usually we will have FQ1 times Q2. But now we have a cocycle here, so twisted means here I have tau theta Q1, Q2. Okay. So that's the complete formulation of a Maxim machine. So what can we learn from this Maxim machine? So this Maxim machine kind of tells us we can consider the representation category of H representations. This is equivalent to the following category. We're going to have this G hat with this Q action, so this action group, right, together with this kind of cocycles. So that's kind of what we have. So there's a two cocycle, U1 value, two cocycle about this. And the H representations corresponding to representations of this guy. So that is the next slides I'm going to show you. So basically, I would like to formulate this kind of representation theory using a more modern language, using the corresponding algebras. So the H representations correspond to the representations of this group algebra, and representations of this guy correspond to the representations of the twisted group algebra. So let me explain to you what do I mean by group algebra and then the twisted group algebra. So the group algebra is the standard we are consider algebra, just the functions on this group. So maybe I'll write C of H, but with the convolution. Okay. So by convolution, I mean we have F composed with G, say evaluated on some element H. It is defined to be F of alpha G beta such that alpha beta is equal to H. Okay. And so that is for the group algebra. Now what is a twisted group algebra? Basically here we put the cocycle we have. And the property that this is a cocycle exactly tells us this twisted algebra is again associative. This is again a nice algebra we can consider, so maybe tau. Okay? So here I'm using another kind of modern language about this equivalence of categories. So I'm using this, which has been mentioned in our conference. It's called the Morita equivalence. So if you haven't heard about this, basically it tells us the representation category of the algebra CH is equivalent to the representation category of this algebra. Okay, so basically that is the functorial way to define Morita equivalence. And this also tells us there is kind of a duality between the group H and that group height. Okay? So that is kind of the simplest example we can think of for this duality of gerbs. Okay, so just to explain to you maybe what's going on here, I want to make a toy example. This probably is familiar to most of us. So I'm assuming that now Q is the quotient group is trivial. So we have H is equal to G. In this case, what do we know? We know that C of H is just group algebra. Now for this one, we don't have Q anymore because Q is trivial. We only have this G hat. So this G hat is just H hat. Okay. What we are saying is this group algebra is Morita equivalent to the algebra of functions on this set. So this is actually a standard result from group algebras. We know that the group algebra has this following decompositions. It's a decomposition of the matrix algebras. And the representation theory of matrix algebra is exactly Morita equivalent to constant. Okay, so this is in particular when we have, say, G is abelian, then each E row is a vector, is just a line, then we really have CG is isomorphic to CG hat. That is usually called the Fourier transform. Okay, so what we are doing here is basically a kind of a more general version of this kind of punctuating duality between G and G hat. Okay. So I apologize here. I have a lot of algebras to start with, but in order to explain this, physics conjecture, I have to do this because they usually use these terminologies, G, G hat, and all this. Okay? So any questions so far about this part? It's probably not very familiar to us since we are geometers. Okay, so now I want to come to the second part of my talk, which is about the gerbs and the groupoids. So basically, I would like to explain to you the second part of my title. What do I mean by the duality of gerbs and groupoids? So, so in order to explain to you gerbs, I guess Marco has already given you some ideas. Give you probably more refined definition. I'm trying to remind you the G bundles first. So what is the principal G bundle? I'm using the check constructions. So what we can have is we're going to have a covering of a manifold such that the G bundle is trivialized on every chart. Then the data of these charts glued together is defined by G value of the one cocycle here. They satisfy this condition. So now to kind of relate this formulation to my later gerb formulation, I would like to point out to you, given an open covering of the manifold, we can define this check groupoid. Okay? So this groupoid is Morita equivalent to the original manifold. Okay? And now, using this check groupoid, what is our cocycle? This cocycle is basically a function on this groupoid. And what we are saying here, this property exactly tells us this is a groupoid one cocycle. So another way to formulate the principal G bundle is basically it's a G value of the one cocycle on the groupoid, check groupoid. So now I would like to make this kind of analogy one step further. I want to consider not just the bundles, but of gerbs. So essentially, you can say it is a BG bundle over the space we are considering. So again, I'm giving you the check presentation. So basically, we're going to have an open covering of our space. Now, this data just show up in Marco's talk. So on the double overlap, we have these automorphisms of groups. And on the triple overlap, we have G-valued functions. And they satisfy these compatibility conditions. Okay? So this is kind of a local presentation of a group, of a gerb. So now I would like to give you some examples. So the first example, actually I've already showed you, so let me remind you, this group extension case. Now what do we have? We have, excuse me. Where's my book? I don't see my book here. So what do we have? For every Q, a map from alpha map Q to out of G. And also we have for Q, two copy of Qs, we have a map from two copy of Qs to G. And you can see here this property. This one is exactly this first identity we had for the gerb. Maybe is exactly this property. And the one I didn't wrote for the extension case is exactly the C alpha beta satisfy these conditions. Okay? So what do we have for the G extension is exactly a G gerb. Okay? So now I would like to continue my check presentation of a manifold. Now what is a G gerb over a manifold is basically an extension of the check groupoid by this groupoid. So here is this groupoid is just a bundle of groups G. Okay? So I must say, the idea of gerbs was developed first by Giroux, and this kind of extension ideas was developed by Brzezinski. Okay? And in general, this is about the gerbs on manifold. What I will do is will be gerbs on orbifold. So in general, what's the general scheme to consider gerbs is we're going to try to represent a space by a groupoid, and then a G gerb over that space X is an extension of that groupoid. Okay. Okay. So let me give you a kind of an example of G gerbs on an orbifold. So here I'm considering, to make the story simple, I'm considering a special type of orbifold, which is a global quotient. So I'm having three groups, which we have been talking about today for 30 minutes, G, H, and Q. What I'm requiring is G acting on M trivially. So you can think like this G is in the stabilizer group of the total manifold. And now we have this extension of groupoid. So in particular, we know this action groupoid is a presentation of the orbifold M mark Q. So what do we have? Using the exact sequence G, H, Q, we are having a G gerb over this orbifold M mark Q. Okay? So in general, if we are giving an orbifold, what do we do is we're going to first of all present an orbifold by a proper étale groupoid. So what I guess I should explain to you what do you mean by proper and et al. So a groupoid have the following map. It can be the structure map to G0 cross G0, the source and the target. So by properness, we are requiring this map is a proper map. Okay? And for et al., we are requiring, both S and T are local diffeomorphism. With these two properties, we are saying our groupoid is called the proper et al. Groupoid. And it was, Modic and Planck who developed the theory about for every orbifold we can find a proper et al. Groupoid presentation. And once we have such a presentation, then we can have consider G-gerbs as a G extension of groupoid. Okay? And so in general, this kind of groupoid presentation of the orbifold is not unique, but they are Morita equivalent. They are all Morita equivalent. So we have to consider Morita equivalent G extensions of orbifolds. And this kind of notion of Morita equivalence of G gerbs and using the extension theory, I learned them from Camille Laurent and Mathieu Stilon and Ping Xu's paper. Okay? So that is the general framework we're going to work with, a G gerb over an orbifold. So next, I would like to define you this dual space. I haven't told you what is the dual space. The dual space now, remember, we have Q acting on G hat. This is a real action. So now what we can do is we can consider this product manifold and take the action groupoid again. This is going to be my new orbifold. Okay? So this is my original orbifold. And I have a G gerb. Let me call it Y. This is M mod H. Now I'm constructing Y hat. It is M cross G hat mod out the Q action. Okay. So that is the orbifold. Then what do we have? Remember, we had a groupoid to 2 cocycle on this groupoid, and we can pull back the cocycle to the new groupoid, and this new cocycle on this new groupoid defines a U1 gerb on Y hat. Okay? Because there is a natural groupoid morphism from this groupoid to this groupoid by forgetting the component M. And we can pull back a cocycle on this groupoid to this groupoid. In particular, what we can observe here is the pullback cocycle must be locally constant. So it's a torsion gerb. So what we will have is a torsion gerb over this orbifold. Okay. So from the Maxim Machine, it kind of suggests us the G gerb Y over B is kind of dual to this G gerb, U1 gerb of Y hat, on a Y hat. Okay. So here is the kind of conjecture we learned from some string theorists. So what they kind of computed is they computed some kind of a generating function on some gerbs, kind of special type of gerbs, and what they discovered is the generating function for the dual two gerbs are isomorphic. So that is how do they come to this conjecture? And what we are trying to formulate this conjecture into the following principle is the topology of this G gerb over Y of G gerb Y is equivalent to the topology of this Y hat twisted by this U1 gerb tau. Okay. So let me maybe I should give you an example of a gerb which shows up very naturally. So I guess there's a notion called the reduced orbifold. Which means for the stabilizer group of every point, they act non-trivially on a tangent space. So for group in the stabilizers of every point, acts. And so maybe I should formulate it. This map is an injective map. So there's no global stabilizer groups. But in general, we know there are orbifolds which, do have global stabilizers. For example, the orbifold I just wrote, M mod H, this has a global stabilizer. And so there's a very nice theorem proved by Ika-Modike and Planck. They were saying this kind of groupoid, this kind of orbifold can always be presented as a quotient of a manifold by a compact group action. So this G is a compact group. So it's kind of a global quotient. So now, in general, if we are having a long-reduced orbifold, I'll use Y. So what's explained in Kai Barron and Luhi's paper is there is always a group, finite group G and a reduced orbifold, say B, such that Y is a G gerb over B. So for arbitrary orbifold, you can always find this structure. Now we can try to use our duality kind of a principle to apply to this G gerb. What do we have? We're going to have a new orbifold, Y hat. And from that property, you can easily see this new orbifold, Y hat, is actually a reduced orbifold. And on this reduced orbifold, we have a gerb tau. So now, again, we can apply this Modike-Planck result. We can present this Y hat by some global quotient. And now we have a gerb on it. So in some sense, this tells us if we want to study the geometry of an arbitrary orbifold, what we need to do is we can just consider a global quotient by a compact group together with some U1 gerb. Yes? It's the orthogonal group.
No, the one on the left.
Here?
Yes.
Here you have to take the global stabilizers of the, if you present, maybe we can discuss later about this. Yeah. Okay. Okay, so that is the kind of a very natural example to have. So now I would like to present you some results. What we can say about the geometry, really what we can say about this duality. So the first result is kind of a repeating of what I have before. So remember, I want to. Okay, now it's. Remember, we have this extension of groups. So in the language of stacks, what do we have? We actually have a fibration of stacks. We have this stack B, a point walled out by a Q, and we have a stack H. Corresponding to H is the B of H. So what we can have is this B of H is a G gerb over B of Q. That is the kind of orbifold, the G gerb we have. Now we have another kind of a stack, the orbifold, the G hat mod Q. I must say we have to think of this quotient as a stack. Otherwise, this theory doesn't make sense because the point over point, there's no natural theory to have. Okay? So what we have is we have this Morita equivalence. In particular, the nice thing we can have is we can have a nice Morita equivalence bimodule. Here is a bimodule. Stefan will probably explain to you more about this. So this kind of bimodule really give us the functor the equivalence functor between the category of representations.
Maybe you will use this pointer.
Oh, thank you. This one? Okay, thanks. So I particularly mentioned this because I'm going to use this later. Okay. So that is the first kind of motivating result. Now we can, first of all, try to extend that. That's a kind of a small step. We can go further. So what is a natural generalization of this? H, group algebra H is going to be the groupoid algebra of this groupoid. So in the same way, the groupoid algebra is defined exactly like this. Again, the functions on the groupoid and the convolutions. Okay? And similarly, we can have this tau-twisted group-out algebra is again defined like this in the same fashion. Okay, again, you can prove that these two algebras are Morita equivalent. Okay? So that is a small extension of what we had before. And now, in the next step, I want to introduce symplectic form or the Poisson structures. So this step is really useful. I'm going to explain to you why do I need this. So I'm assuming that on M, I have a symplectic Q-invariant symplectic form. It must be Q-invariant. And once we have that, I also assume that we choose a Q-invariant symplectic connection. Once we have this data, we can construct a deformation quantization of the symplectic manifold M, which is Q-invariant, Q-equivalent, if you like. So now with this, we can again define kind of a cross-product algebras. So again, we can extend this result to the quantized version. We again have Morita equivalent. Okay. So in some sense, we are saying for the noncommutative geometry of this, groupoid or this orbifold is equivalent to the noncommutative geometry of this orbifold with this gerb. Here we are kind of saying the noncommutative symplectic or Poisson geometry of this orbifold is equivalent to this one. Okay. So one more result. So if you are not interested in these algebras, you can try to play with sheaves. So if we consider, so this result works for any categories, C infinity or holomorphic or algebraic. What we can say is the category of sheaves, abelian category of sheaves on Y is actually equivalent to the abelian category of tau-twisted sheaves on Y hat. So here it must be tau-twisted. Okay, so by tau-twisted, basically, if we have a co-cycle on the groupoid, we're considering the sheaf now not Q-equivalent, we're considering tau-twisted Q-equivalent. That's what do we mean by tau-twisted sheaves. And what we can prove is, again, these two categories are equivalent. Okay? So these are kind of the generalization of the standard Maxim machine to groupoids. So now what I want to explain to you is what kind of geometric results we can conclude from this kind of algebras. Okay. So the first result you can say is about this K-theory. So if we have this algebra, the K-theory of this algebra is well studied by operator algebras. They are just the H-equivalent K-theory on the manifold M. It's the K-theory of the orbifold, of the quotient. Yes?
Are you considering sheaf of K-vector space or sheaf of OX?
So, you mean this one? So here I'm considering sheaf of OX modules. Yeah, right. Not just vector space. Okay. So on the other side, if you look at the twisted group algebra, the K-theory was developed by Tu and Shi. They called this twisted K-theory, which is related, is along the line developed by Atiyah and Ziegel and many other people about the twisted K-theory. So what we can conclude from this Morita equivalent of algebras is the K-theory of the gerb Y is isomorphic to the twisted K-theory of orbifold Y hat. Okay. So you can take this as a kind of a K functor on the algebras. To tell you something more, I need to introduce some terminologies. So first, terminology is about this inertia space, which is kind of the quotient of fixed point subset by Q. And on this space, we have a natural function called the codimension function, counting the embedding of the fixed point subset into M. Okay. So I must point out, this guy, this disjoint union of fixed point subset, this is not a kind of a true manifold. It should be viewed as a stratified manifold because M gamma may have components of different dimensions. But if we look at the kind of the gamma components, gamma orbit, then every orbit is really a orbifold. Okay? So another function I would like to introduce on the inertia is this something called the H function. So this is, you can view it as kind of counting, weighted counting of the codimension of the inertia. So to do that, we need to put a almost complex structure, gamma equivalent almost complex structure on the manifold M. With that, we know this tangent space now is a complex vector space. And all this gamma group, this stabilizer group, this gamma is fixing this X. So gamma acts on Txm, so it can be, the gamma is of finite order, so Txm is decomposed into eigenspaces. So we are basically counting the codimension according to the eigenvalues. And this is kind of the physics called the fermionic shifting in the twisted sector of conformal field theory. Okay. So these are the two interesting functions I would like to mention. And the next thing I want to remind you is about the tau twisted cohomology on the inertia. So basically, if we are given a flat U1 gerb on an orbifold, we can introduce a flat line bundle on the inertia in a very concrete way. And the cohomology, twisted cohomology, basically is the cohomology with coefficient in the line bundles. Okay. So why do I need all this? So that's the following statement. So first of all, when we compute the Hochschild cohomology of this algebra, is the joint work with Flam and Postuma, is isomorphic to the cohomology of the inertia with the degree shifting L. So I must say, here the advantage of working with Hochschild cohomology is we have exactly the degree for every L and also the fixed degree here. So in general, if you don't consider Hochschild cohomology, such a computation was already done by, probably traced back to Berlinski or Bloch-Getzler. Many experts have been computing the periodic cyclic cohomology of such an algebra. So, and if we have a tau twisted algebra here, it's computed by this tau twisted cohomology on the inertia. So this is a kind of again, if we consider periodic cyclic homology, this was computed by Tu and Xu. So now, since we know the algebras are Morita equivalent, their cohomology are isomorphic, we can have the following conclusion of the isomorphic of vector spaces of the cohomology. Okay. So that's the kind of direct applications of the kind of cohomological functors on the category of algebras. But what I want to present to you next is something we can even do something more than just applying this kind of functors. There's something more interesting we can get out of this, noncommutative algebras. So the first result we can consider is once we have a Morita equivalent algebras, if we are given an explicit bimodule setting up the Morita equivalence, one can have an explicit isomorphism between the centers. Now, what are the centers of these algebras? So for this group algebra, we know they're just the class functions. Very standard in the representation theory. So now for this groupoid algebra, we can pass to these algebras, this tau twisted group algebras. Then the center are just the tau theta regular class functions. Basically, they are kind of functions on the conjugacy classes. But now by tau twist, we have to require when we act by conjugation, this tau has to show up there. Okay? So now what do we have? We have isomorphism between the centers. So we can identify the centers and also even identify the trace. Okay? So here by the trace on the group algebra is basically taking one on the identity element and a 0 for any other group element. So why do we interested about this? Because when we have an abelian algebra with a trace, and this kind of abelian algebra with a trace, the trace is very nice, and they define Frobenius algebras. So if you haven't heard about what is Frobenius algebra, I can explain to you later. I'm running short of time. So what we have is we really have an isomorphism of Frobenius algebras. And this Frobenius algebras, if you are interested in Gromov-Witten theory, they are the kind of a genus zero Gromov-Witten theory for this orbifolds. And what we can do next step is we can even extend this isomorphism of Frobenius algebras to the full Gromov-Witten theory on this orbifold and on this BQ theta with a tau-twisted Gromov-Witten theory. So this is through kind of the cohomological quantum field theory arguments. Okay. So here we have to use some kind of simplex topology, but the fundamental thing we have to use is this isomorphism between centers. That's kind of the foundation which provides us a nice isomorphism between the Frobenius algebras. So I have 1 more minute. Maybe I skip these details and tell you the answer. So remember, I had this result about the Hochschild cohomology. We know that these two cohomology are isomorphic as vector space. But I also introduced this H function. So how about this H function? So that is the purpose of the theorem I'm stating. So what we can improve is, out of the isomorphism we have on the shifting by L, we now can improve it to be the shifting by the H. So remember, H is not an integer in general. It's a rational number. So we can even improve the constant, the coefficient from CH bar, to C. And more interestingly, we can even prove these two are isomorphic as some algebras. So this algebra structure is defined by some kind of integration on some moduli space of curves that is really called the Chen-Ran cut product. Okay. So this is kind of the degenerated version of the general Gromov-Witten theory. So the most important step here is, through this Morita equivalence bibundles, we are able to write down a very nice, very close to the Fourier transform map of the cohomologies. And then we have to play with we have to do some more computations and also even study of the moduli spaces and the obstruction class of the Euler class of the obstruction bundles. With that, but this is the kind of the fundamental starting point with this result from the noncommutative geometry and the Poisson geometry. So that is the result I want to present. So let me just leave these slides and I will stop right here. Thank you for your attention.